All right, so we're gonna get started here at 10:30, even if everyone's gonna be a tiny bit late. Okay, there we go.
I have a small class through this now, so I can do that.
Yeah, last 2 weeks, you know.
Yeah.
So yeah, anyone who has homeworks, if they want. Want one or no?
I'm just trying to decide if I want white or black. It's really easy.
Okay, all right. I can make it easier, white or black? There you go, white or black.
Oh, stickers.
Okay.
I just stuck the white.
Thank you.
First. All right, I might have more, but they're in the office, so if you have homework. Use that. I have candy too, yeah, we can have candy. Okay. Alright. So for today, we're gonna finish up discussion of radiation. We're gonna talk a little bit about why the atom doesn't decay. And then hopefully we'll have enough time to start special relativity. But considering, you know, all my best laid intentions never work that way, I'm gonna guess that probably we only get through why the atom doesn't decay. And my hope is that we can start special relativity next Tuesday. And even though we'll have a homework on what you're seeing right now, so you're turning in chapter 10, homework 10 type stuff. And you'll see that homework 11 is chapter 11 type stuff. The last one, the special relativity homework, will be a bonus one.
Okay.
So if you're thinking to yourself, oh my God, how could I possibly take this in 1 week and turn it around? That's the right instinct. But I think if you've ever wondered how special relativity came to be one of the most advanced topics, it's because it's a culmination of both electromagnetism, dynamics, and then, you know, things moving at the speed of light, which was not a concept that we really thought about until the early 1900s. Are people planning to take, no one in this class would take 2300, Ash was 2300, right? No, are planning to take it next semester. You are?
Yeah.
Okay, interesting. They might have to cancel because I think it's undersubscribed. So tell your friends. Otherwise, I'm debating getting 82 or Dr. Wimberly to teach a special/general relativity class for undergrads. Do people want to take that? Okay. Yeah, that's pretty cool. Yeah, all right, okay, all right, good. Okay, but before we can get there, we have to talk about, so we were discussing, we have charges, and in the homework you just saw, there's a charge and it's sitting there, a point charge, and we were looking at the different V's and A's for a point charge. And in 10.7, you probably found that a moving point charge will create B fields. But what happens to a point charge when it's not moving?
No.
No B field, right? Okay, so we have this requirement about motion. And then we said something along the lines of, well, you have a dipole, and let's say you have a magnetic dipole, it's moving up and down, or it's rotating in some way, and it's in some way the dipole moment is changing. That can create radiation. So there is a prescription now for taking a charge and for moving it, right? But if it moves around like this, then perhaps, you know, motions in a wire, that's not going to create radiation at long distances. And one of the questions we have to ask ourselves is what happens if you accelerate or decelerate a charge? Okay, that's the question we're going to start with. And in particular, this will explain a phenomenon that is fun and creepy and is a German word. So we're going to discuss what's called Bremsstrahlung radiation or braking radiation. And this is the creepy blue glow that comes from reactors. So if you ever look down on the Chernobyl reactor, it will glow blue. And we're about to find out why. How do you spell that? Good question. Yeah, you're gonna want to type that into Google because I'm not a very good speller. Okay, so let's start with thinking about radiation from a moving charge, okay? And it's gonna be some arbitrary path. So we're gonna start with some charge Q. Okay. And it's gonna have some path, it's gonna end up over here along that path. Okay. And then this is Q at some later time. So this path we're gonna call W. Okay, and recall that we're gonna use the retarded time here, because when we observe the particle on its path, it has then moved. Right? So light that would travel to us, radiation that would travel to us, is going to reflect where it was, not where it currently is. And let's use our handy dandy eyeball. And we're gonna use some arbitrary coordinate system. So this is to the origin, it's called the 0, 0, in whatever arbitrary coordinate system you want to. And so this will be the distance to us, and this is gonna be that weird cursive R that everyone hates. Okay? All right. So this is the distance to it at the retarded time. So this is the location. Let me spell that right. At. And then this is where it actually is. All right. So two things that we want to think about when we have radiation from a moving charge is that it must be accelerating, right? So when I say moving charges, you have to put these two conditions on it. Because we see that moving charges in a wire don't necessarily produce radiation at long distances. So the first one is that there must be acceleration, or you get no beam. All right, I say you just get beam. Okay, so if you have a particle moving in a loop, right, you have a preferred direction, and then you have B field that comes out in this way and goes back in the other. And the second is that it's going to follow the general properties we've seen before. So we're going to say stuff like E is going to be perpendicular to B. So this would mean that it's transverse, oops, to the propagation direction. And also, we're going to say something like this, E naught over B naught. Seen this before? Remember this one? E naught over B naught. What's the relationship of their amplitudes? Like B or whatever.
Is it V?
Yeah, but B in this case for light is
C?
Yeah. All right, so there's a relationship between the two amplitudes, E and B, and that's just C, right? That's what we saw when we were looking at these. So generally speaking, we're gonna have some fun stuff here. You're gonna have something like the E vector over the B vector is going to be 1 over C. And we're gonna use that funny R, this one here, crossed into B. Okay. And of course, we can say that S, the pointing vector, is still what the pointing vector is, 1 over mu naught E cross B. Okay. So this should give us everything we need in order to describe the motion of, the radiation at infinity. So if I can use this relationship here, we can put that in here. So that allows us to say that this thing would be, well, how do I solve that? Which one do I want to solve for? Yeah. So if I look at this and I want to find the pointing vector, what does the pointing vector do again?
Direction of the energy flow.
It gives us direction and let's build the diagram again. Let's build the diagram. If I want radiation, okay? Radiation is down here. And that is what property? What does radiation mean?
Oh, something going to infinity.
What goes to infinity?
Energy.
Energy or power to infinity, right? So this is power not equal to 0 at infinity. Good. And how do I find it? What's that? From the pointing vector, right? So this goes back upwards towards S. And how do we find S? In B, good. How do we find E and B? A and B, which one goes where?
V for E.
V for E, good. And then A, and then
Q, rho, and J.
okay, so that's the beauty, right? Is that we can go from the charges, we can go from the currents, and we can get radiation if it exists. And what's the requirement here? What are we looking for with respect to R? It's got to be at maximum 1 over R squared, right? Okay, so if it's more than 1 over R squared, let's do it like this. If it's more than 1 over R squared, then we're gonna find out that we don't get radiation, because when we hit it with the dot dA, we're gonna have too many lengths, right? Okay. Okay, so let's go ahead here. So I have my pointing vector, which is bringing power to infinity. And I have E and B, and here I have a nice relationship. So I'm gonna go ahead and put this in. I'm gonna rewrite this one as 1 over mu naught C E crossed with R cross E. That looks horrifying, right? Is there any way out of it? Double cross product?
Those are cool.
What was that? Back cab, very good. All right, so let's write this down. Let's assume that I've already written it perfectly here. It's gonna be like 1 over mu naught C E squared in the R hat direction minus R hat dotted into E in the E direction. Right? So we can notice one thing. That is, if we look at our choice of coordinate system, we say, well, Prismani, why did you put the origin way over here? That's kind of silly. That's an arbitrary choice. And we can think about, well, if we just set the origin here to start with, we know that it'll change later. But at the very beginning, we might notice something about the directionality between R and E. So if you have a wave, we've seen this before, how is the E, B, and directionality, how are they related to one another as far as direction goes? See some hand like this? Left-handed hand? What is this one? Okay, so let's say this is E. This would be E. Are they ever like this? Can I get E in the directionality in the same direction? No, they have to be tangent to one another if they're waves, right? Especially if they're self-propagating. So you can make this E, and I could just rotate my hand however I want, right? This could be the D, but this could be the Z direction, and then this is E and B, but they're always orthogonal to one another, right? Okay, so the first, oh, now I have to get rid of this. So the first thing we have to say is that E has to be perpendicular to R. Right? Cool. And at the very beginning, we can say that S then must be 1 over mu naught C E squared in the R hat direction. Okay. So you can imagine this becoming very complicated very quickly. if the charges were moving very fast. And that's not this class. This class would be charges moving rather slow. So if we want to get to special relativity, we don't really have enough time, but if you had a full semester, you could see what happens when the fields are moving close to the speed of light. And it's really cool. But we don't have time for that here. So let's first imagine that you have something like the E radiation for non-relativistic. So when I say non-relativistic, I just mean not moving near the speed of light. Okay, so this is gonna look like this. Q 4 9 R R hat dotted into U. Now what's U here? Speed? Yep, yeah. We're gonna use the same notions that we have in the past. So U here would be the movement of the particle. So W dot will be U. The path of the particle is W, and then the speed of the particle would be U. Okay. And this is gonna be different than if we were to consider, say, the velocity of the wave that's coming out, which we know to be C. So instead, U is the motion of the particle. And what we're saying here is that U is much, much smaller than the speed of light. Okay. Okay. What's A there? What's always A? There you go. Okay, so we're doing dynamics again. So we're going to use all of our old friends. So A is the acceleration. Okay, so this one here is the acceleration from the moving charge. Oops. The acceleration is 0. What's the radiation here? Good. I built it right in, right? This magic came down from on high and just perfectly is 0, right? So this is by definition, of course. And the important thing to keep in mind here is that all of the pieces that we want, so this is the motion of the charge itself. Right, position of the charge and the acceleration of the charge. We could drive this, but I don't think it's worth our time. It's in the book, and if you really, really care, we can do it in office hours. Okay, but there's some really important terms here, right? So in particular, the motion of the charge here, we're going to define as CR, because recall that we're looking at the retarded position and the velocity of the charge. So this would be in its frame, and without getting into too many of the details here, it is important to keep in mind that the way that we view the motion is going to depend on our reference frame. Okay. Okay, there are other fields. And if you wanted to write this out fully, you will see that the other pieces that we've seen before, whether that is charges moving around in a circle, they produce some fields nearby. And those fields are not the ones that we care about. So even though I just deleted this entire piece that talks about how we get back to radiation, some of those fields that are produced, they fall off faster as you go off to infinity. So this is the only term of the radiation terms. There are other terms. This is the only term that will survive to infinity. Is that obvious from this? It's not obvious? Look at the powers of R here. Have 1 on the top, 2 on the top. Right? And I have 3 on the bottom.
Yeah.
So that's about 1 over R. And what was our requirement?
Plus one over R.
That it's at least 1 over R squared, right? Because that way it's a constant. So this thing's even growing. And we'll see.
Isn't that E not S?
Right, yeah, 1 over R, yeah, okay, good. But what 1 over R squared.
With
Yeah, and this one you'll see, we have to work out these in detail. We're gonna have some individual terms that we'll talk about. But you end up with, this is the only term that contributes to the radiation field. Okay. Okay, I also made. I guess I should say this somewhere. I'll write it down right there. Okay. U or V much less than C. We call that non. Relative statement. Okay. We have another nasty double cross product. What's that?
Back up.
Yeah, back that again. Okay, so we'll just write that one out and I can write that S is equal to 1 over mu naught C mu Q acceleration of the particle. This was a different way to write that. Let's simplify this slightly. I could pull the A's out. 1 minus cosine squared is
Just, sine squared.
sine squared. So let's write that. Let's simplify this a lot. Mu naught Q squared A squared. 16 pi C. Then I have sine theta over R squared. Good. All right. So let's see if this makes sense. So of course we built into it that A being 0 is going to give us nothing. Does it matter which direction the A is? No, because it's squared, right? So if we're slowing down or we're speeding up, we're still going to get radiation. It's the acceleration that matters, and that was the original part here, right? Okay, what are the other pieces here? So it's in the direction of this weird R. That's kind of what we expected. We're getting radiation from where the particle was, not where the particle is, right? Does anyone have a sense for what that function is? S theta over R? Sine theta over R? Quantity squared. Right, why don't we grab whatever we have available to us, see what that plots out as. Remember that we're working in a cylindrical coordinate or a spherical coordinate system here. Yeah, I mean, we can do it all by our computers, and you may find that, you can get it on Wolfram Alpha. I don't know if you're using Desmos,
I would
they
think.
didn't like it,
I don't know, I couldn't figure it out.
okay.
They don't like it.
All right, well, we can do this in office hours. I can show you how to use the command prompts a little better, but we can do by hand.
Yeah.
Right? How do we, no one likes hand. Okay, so how would you do it by hand?
Wait, so you use like various, like,
Like,
what do you think?
Yeah, plug in a million numbers, right? And that would be the only way to do it, is that correct? No, not a million numbers. How many numbers do you need?
You need like,
Let's take R and make it unity. Okay, so we'll say at a normalized vector of 1, right? Because sine squared over 1 is pretty straightforward. Right, now we'll know that as we go farther out, whatever that shape is, it's gonna be similar, but it's gonna drop like 1 over R squared. Okay, so whatever the magnitude of that shape is, it's decreasing in intensity. Right, as you go out. So we understand that 1 over R squared part. So what does the sine squared part look like? Not like a circle, not like a circle. Cosine squared plus sine squared is a circle, right? So what does sine do at pi over 2?
Zero.
I was fighting. Who's right here?
One.
It's 1, okay. So over here, it's at 1. Good. That's pi over 2, right?
Yeah.
Okay, and what's it at 0? 0, okay, good. What's at pi over 4?
oh,
It's like square root over two.
Sort of 2 over 2, so not quite out to the unit circle, so somewhere in here, right? And what about on this side, whatever that one is, 3/4 of pi.
should be negative. No, it's positive.
Positive, very good. All right, there you go. All right, and then down here,
Got
It's squared.
yeah, you can just copy it, right? Because it's sine squared.
Yeah, it's
Okay, so interestingly enough, you get this fun little,
She's like.
it's an 8,
Thursday.
right? We just did this on Tuesday, except we did cosine squared and it was flipped over. Right, that was our infinity sign. Okay, so now we're thinking to ourselves, well, okay, what does that mean for one? That means nothing to me, right? How am I orienting this thing? So let's think about the orientation really quickly. We're gonna use a right-hand rule again. So this is R, and then these will be theta and phi, right? They're still gonna be perpendicular. No? You don't like it? Okay, so let's imagine you have a propagation direction that's like this. So I'll be the charge, and you're all gonna be the observers. So I'm moving, right? And I'm leaving behind, right? I'm accelerating, and so now where my picture was, imagine my image was here, this is sending out the radiation. So that's the R hat direction towards all of your eyeballs, right? Okay, so this shape here, okay, the sine theta is going to be perpendicular to the direction, right? Because theta hat will be perpendicular. So this is a donut, okay, that has nothing in the middle. Is that weird? Okay, so what does this mean? This means if I'm staring directly at where the particle was, I don't get any radiation to my eyeball. But there is a donut of radiation that is increasing and going outwards. Yeah, it's very weird. That's the uncomfortable feeling you should feel. Okay? So in fact, what we see when we're seeing these particles come out of a nuclear reactor, they're slowing down in the water and they're all creating cones. These cones are expanding. And even though maybe you're looking directly at one of them, its friend who's nearby, who's also slowing down, is the one contributing to the blue light to your eye, right? If you can imagine that it's a little bit of a curve to it. Does that make sense? That radiation is still getting out to infinity, still getting to your eyeball at very large distances, right? Okay, so that's the functional form that we see here. So let's write what it looks like in P talk. How do I write P? Power out of infinity, what's that?
The integral,
The integral of,
S of A.
very good. All right, so let's do that integral. I don't like it. Okay, so you would see that there is an area here. What's the area of a circle? Surface area of a circle?
Yeah.
4 pi r squared. Okay, so that's gonna get rid of one of ours here, and we're gonna end up with something that looks like this. Mu naught q squared, a squared. And you're gonna be really upset that this is a 6, not a 4, but remember that we have a sine squared that we're averaging here. Okay. And that's it. So this is called. I think it's right there, but I think this is how you spell it, the Larmor formula. And interestingly enough, this looks like the radiation that comes from a dipole. It has the same functional form, where the acceleration that we had before was that rotation, right?
So maybe a dumb question, but you said that the surface area is 4 pi, and then, 4 divided by 16 should be 4, so why?
Oh.
That's-
It averages out the sign.
Oh, it's a-
That's good.
Yeah, it's okay. There's a little half step in there where we're not really looking at S, we're looking at the expected value of S, right, which is those brackets, the curved brackets. That's the time average. Right. All right. So you've all believed me. Right? And no one's like, I mean, a little uncomfortable with the numbers, maybe a little uncomfortable with some of the shapes. But you're not screaming. And you should be screaming. Okay. Not something I did wrong. You should be upset because I just told you that accelerating charges emit radiation. Right? Okay. Now I want you to think for a few seconds why this should make you very uncomfortable. No. Our phones are not giving us cancer. That's a different type of radiation. It's non-ionizing. Okay. What, when we're thinking about some of the greatest scientific developments, motivational developments, right? So if you think about how did quantum mechanics come about, how did special relativity get joined to physics? These all come from, at first, something that seems paradoxical. So no one ever looked and said, oh, you know what? Stuff at very small scales, that should just be quantized. No one just guessed that. They had to first be presented with a problem that they were trying to solve, right? So what problem was Bohr trying to solve? Let's think first about what the classical view of an atom was. We had this idea, right? 1600s, 1700s, they were doing these experiments with needles, right? They found magnetism, they found that there was individual units of charge. And they did that really early on. 1700s, they were using like oil and suspending things to get the mass per unit charge. They were measuring the electron way before we had electronics, right? Before we had electricity in a conventional sense, they had measured the charge of the electron. Okay, so now I know the charge of the electron, and you understand that type of stuff there, chemistry, which we don't understand in this class, but people have understood before. Okay, so you have these two pieces. And they said, well, the idea of the atom is not that it's all spread out, right? So it's not like a loaf where the atom is spread, they're concentrated, right? And the classical view of the atom was what type of atom? Yeah, classical.
That's what.
What was that?
I said, I was wondering if it was the plum pudding one, because that was one of the.
Yeah, the plum pudding was the original one, it was like smoothed out.
Oh, then it became.
And then people found out that there was individual charges.
So that's the form.
Yeah, well, what does that mean? What is the Bohr model?
And they're part of
The particles and the particles that do what?
orbit.
Orbit. Okay, so here is where you should start to feel uncomfortable again. Because if you claim, you're all claiming, right, that that the atoms are orbiting, that there is a proton and an electron. Let's say the proton doesn't move. Let's say the electron is the only one moving. What happens as it orbits?
It changes.
The acceleration changes.
You didn't claim that. I didn't claim that. You claimed that. You said it was orbiting. I think it's a plum pudding.
So the acceleration changes.
Ah, so the fact that it's moving in direction is still a form of acceleration. And all of these things are true, right? So it's at some distance from the observer, it's moving with this constant speed, but it's changing its direction, and this is something like circular motion, which we can calculate. Okay, so all atoms should then radiate and therefore decay, correct. All right. So this is what makes you uncomfortable.
But we know that there are stable atoms there.
Hopefully, we've seen stable atoms, right?
Yeah.
The fact that I can in fact like do this, right? That's an indication that atoms are stable.
I mean, don't they all technically have legs, so they are decaying?
Not for the same reason, though.
Oh,
That is true, but not for the same reason. Okay, so what's the solution? Let's first find out how quickly they decay, right? Because maybe it's not a big deal, right? What?
yeah, so it goes really fast.
Yeah, so that's the question. How fast do they decay, right? Like, this won't be a problem, will it? Yeah, this is gonna work out. All right, so let's start with the idea. So, we have a Bohr atom. So you have, let's draw a picture. I'm gonna get rid of this one, if that's okay. Draw the picture. You have a proton. And an electron. And your claim, not mine, I would never believe this, is that they do this. That's the Bohr version of the atom, right?
Oh, so that's why we have the cloud thing.
I don't even know it. What are you talking about, cloud? I've never heard of cloud in my whole life. Everything's a plum pudding. We don't know anything about this. Okay, so what's the distance here? Well, this is a radius r of 5 times 10 to the minus 11 meters. Okay. Small. It's held together by which force? There we go, fourth one there. Okay, so in fact, the inside of the atom is held together by the strong force. The weak force allows an electron to become, or sorry, a neutron to become a proton, or vice versa. And the attraction here between the plus and the minus is the Coulomb force. Did I spell it right?
Yeah.
Nope,
No, definitely not.
it's OU.
This is why this is not a spelling class. Is that right-ish? Yeah, so
It would.
order magnitude. Okay, so this is the Coulomb force. And we'll recall that they are attracted to one another. But because the electron's going around in a circle, right, it doesn't fall in. So just like a satellite orbiting the Earth, they're attracted by gravity. Satellite's going fast enough that it just falls in, right? Okay, so let me ask a couple different questions. We have P here, that's the Larmor formula. I'm not gonna rewrite it. What's the force here? QE? No. We know what the force is. What's the Coulomb force? You're not wrong. That is the force, but then I'm gonna have to ask you what E is. What?
There's like 2 Q's on top.
Good. Anything else?
Constants,
Constants, very good.
R squared.
Where?
Oh, wait.
It's in the bottom, yes, the farther you
It's
go.
the bottom.
It's the bottom. Okay, very good. All right, so in fact, it looks exactly like the gravitation. And there are deep fundamental reasons for that, but not in this class. Okay. And so that's MA. And what type of motion is this undergoing? Circular motion, so that means that MA has what functional form in terms of V?
Centric. So, and.
Very good. Yeah, so let's write that. So that's also equal to M V squared over R. Right, so this is the idea that this is centrifugal motion. We're gonna hope that that's also spelled right, but if it's not, that won't bother me, right? All right, so we have the Coulomb force is balanced by centripetal motion, right? That's the two forces that are at play. Okay. So let's see, can we write our Lamar formula or more Larmor formula? In terms of A? In terms of the things that we can measure? Okay. So we're gonna write mu naught Q squared over 6 pi C. And then we're gonna write 1 over 4 epsilon naught Q squared over M R squared. Yeah, right? Yeah. No one likes it. That's okay. All right. So this represents the total change in energy, right? This is what P is. So we could say something about how much energy is lost. How do I relate power to energy again? EDT, okay, yeah, so let's write, I'm gonna say DUDT, but that's the same, okay? Okay, and so I'm gonna write the total energy here, U is going to be the kinetic energy plus the potential energy, right? That's the energy of any system. What's the kinetic energy here? Very good. And the potential energy is? The same as the force.
So we ignore gravity.
Yes, we can't ignore gravity.
Centripetal?
What was that, John?
Centripetal?
So the potential energy here, how do we go from forces to potentials? Yeah, it's a very good question. Yeah. Is it an integral or derivative?
It's
How do you go from force to energy?
Yeah,
oh, it's I'm pretty sure it's integral with the speed.
yeah, so let's write this here. So 4 pi epsilon naught, that one comes for free, right? And then Q squared, that's also a constant. And the question is how does it depend, how does it depend on R?
Like ours
Pretty
should
sure
be on
it's-
top.
I'm pretty sure it's linear.
Linear, what do you mean?
So 1/r.
1 over R,
1/r.
right? So if I take a derivative of that with respect to R, you get 1 over R squared, right? Which is your force. So the relationship between potentials V and F is okay. So we can make some mathematical substitutions here. I don't want this. I don't know the V off the top of my head. So I'm just gonna keep using what we've written before. And instead I'm gonna sub in that earlier form. And when I combine the two, I'm gonna get something like this. 1 over 8 pi epsilon naught Q squared over R. And I'm just missing one little thing here. Negative. Negative. Okay. Why is the total energy negative? Well, not yet. We haven't applied any of the power to it. We're just asking what the original energy of the system is. Right, in this circumstance, it has more potential than kinetic. It's a bound system. If the energy were zero, right? Then that would mean the kinetic and the potential energy were balanced. That would be an example if we're thinking about gravity, for example. That would be something like an object comes near the sun, gets going really fast, and then goes really far away and never sees the sun ever again. Whereas if we think still about the orbiting potential, for example, which planet goes faster, Mercury or the Earth? Mercury. Mercury has to go faster because it's deeper in the potential well. So if I want to move down in the potential well, deeper into the potential well, I have to be going faster to remain in orbit, right? Otherwise I fall into the sun. Okay. So here we know that the total energy, maybe I'll write this better. This is the total energy, is the is this amount, and it's negative. Okay. Let me write most of this out for you, and then you're gonna find out the time. Okay, that way we use our brains together. So let's write du dt, which was up there. Okay, so if I combine some of this together, I'm gonna do it on this side, that way it's simple. All right, so let's start with du dt. So that's up there. That's gonna be equal to -1/8 pi epsilon naught u squared over r squared dr dt. And that's gonna be p. Okay. Then how do I calculate dr dt? Well, that's something like. So this is t. And I'm just gonna integrate both sides. If that's okay. I want to put the dt over there, put the drs over here. Flip them all over. That'll put the r squared in the top. So this goes 3c 2 pi epsilon naught mc. And just flip that. Okay. The integral is going to go from r naught to 0. What is that? Grab a friend. One of you do the integration, one of you figure out the constants. Yeah, I want to know what time, how long does it take, right? Because let's think about what we're doing for one more second, right? So this is du dt. So this is the rate of change of the energy. And that is something I claim comes from the Larmor formula. The fact that there is acceleration at all means that the thing is radiating. And we said, well, maybe this isn't such a catastrophe for physics if that rate is really small, right? Maybe it does lose a little bit of energy, but it's like losing only like 1 fraction of an energy every billion years. Then you're like, oh, it's okay. Right?
Yeah, but in the numerator, that have c squared.
You can't give it away yet. Okay, so we have to figure it out. We have to figure it out. Okay, so in fact, what we can do here is we can integrate this, right? We have p and we have t. So we can, using everything that we have on the right-hand side, we can just simply integrate this and we can find out how long it takes for the energy to be dissipated by the Larmor formula.
It's
No,
positive.
it's gonna overall because look at the integral, R
Oh.
not zero.
And then this R cubed over the B.
Yes, okay, so we can do that last, so this part's the easy part, this is what?
R cubed over three.
Negative.
Negative, very good,
Are not.
are not cubed over 3. You might see why I very conveniently pulled out this number.
Wow.
Amaze.
Oh, wait, it's not.
Yeah, like, you can see the mass of the electron.
Do you want me to Google it? Like, sure. I can find my file.
I think that's right.
Yes, or it's just like-
Yeah, that's right.
That's what you're gonna do.
What's
It's negative, the mass of it is. Oh, what's that? What's that?
yeah.
Yeah, so I see a lot of people doing it on their scientific calculators. Why is this not always a great idea?
It's a really big dent.
Yes, huge numbers. Where should you be using these numbers? Where should you be plugging these in?
Somewhere not on my phone.
In your head? No. Oh, you can do this one of 3 ways, right? You can do it on your scientific calculator if you're very careful. You can do it order of magnitude, right? Instead of taking all of the individual numbers, you just put them into the unit systems that you like most. And you say, well, 6.5 times 10 to the negative 23 is basically 10 to the negative 23, right? That's fine.
Yeah.
Right? Order of magnitude will be fine here. But what am I gonna recommend you always do?
Ask us money.
No, we're gonna use Wolfram Alpha. Okay, Wolfram Alpha, you type in the word mass of the electron and it knows what the mass of the electron is in whatever unit system it wants. Okay, so in fact, the reason that we do this is because we are not accountants. Okay,
Thank God.
yeah, thank God. Okay, so in fact, the accounting should be done by the computer, right? And we're gonna do the physics. You're welcome to try it, but we're gonna get a large diversity of answers and it's gonna take 5 times as long.
I'm thinking that's a nice little survey, so I won't walk. Okay, do the thing.
For the Bohr model, is the R that you wrote a distance? I can't quite see that.
Yeah, this one here, this is 5 times 10 to the negative 11 meters.
Thank you.
That's the only distance I put in this problem, or the only number I put in this problem, right? Everything else is a constant.
R not was the board radius?
Yeah, let's call it, let me just fix the notation here, there you go. Same distance. Same.
Yeah.
And do we understand why this integral goes from R naught at the bottom to 0?
Potential.
Yeah, it's decaying, right? So it starts out here and it spirals in to 0.
Okay.
You see that?
Yeah.
All right, I know that ruined the picture, though.
Oh my God.
Yeah, I can type all of them.
What's the-
Well, actually, don't know.
So it decays inward?
Well, that's the claim, right?
I got.
What happens if you sap energy from this system?
It's like to the
It
negative,
gets real tired.
it's like 10 to the negative 11 seconds.
10 to the negative 11 seconds?
Do you wanna see?
Hold on, well, let's write some answers down. Let's see if everyone gets the same thing. So I got T equals 10 to the negative 11.
What?
All right, anything else?
I got 10 to the negative 49.
All right, I got 10 to the
Oh,
negative 49 from
Wait,
Rolando.
is that negative?
How'd you do that?
No, that's what it is. Don't worry, I didn't bring the time since the.
Dude, that's like it's. Dang.
Nothing
What is
exists.
that? It's like double what it is. Where is it?
Yeah, this half is done. Come on, folks.
I don't know how you.
We'll work together. You see, they work together, they moved quickly,
Yeah, that's
right? Teamwork makes the dream work.
No, I don't know there, so.
This is.
Not polite. Right, the only way we know things in science is consensus, right? So we have to see how everyone, if everyone agrees, then Rolando's right, everyone agrees, then Aaron and Isabel are right.
Dude, yours is less than playtime.
Don't point that out. You don't want him to recheck his work, right?
Yeah, I'm not.
We're also looking at the difference in the ways that these were constructed.
That's like 10,000, that's like 10,000 points smaller than playtime.
Then I.
No, that's 100 times.
I think the whole point of this exercise is to prove that subject would exist.
Fun, man.
We're having fun.
Playtime is a bit negative. No, I want it. Give it, give it, give it.
Yeah.
I'm
Right.
sexual. Frogs is a sexual thing. Stop.
Okay, folks.
Use your cue. Like you're charting the cue.
I just.
Like,
Oh,
it's going.
That's all. it is, so. Wait, look, wait.
What do you mean when I do?
Oh, your board rate.
Cube, squared, squared,
Where's your board rate super?
right here. And threes cancel out, but you need to get rid of it there. So just, don't type the three.
Well, this one, it's this one, right?
Yeah, but
Oh,
you,
And
yeah,
then this is the answer here.
Oh, okay.
But
Yeah.
yours is not off by a factor of 3, right? There's
They are, that's.
38 orders of magnitude.
Mine's 3 times his.
Mm,
You know-
Not 3 times.
You
have to
know,
think about the order
11
of it.
times 3 is
Yeah.
40.
No, it's not.
It's 4.
No,
Are you?
Yeah, that's.
Oh, we. Yeah, I agree with you as well now.
Well, what's the number you get?
1.3 e or 10 to the negative 1.
10 to the negative 11.
I got 1.5.
I've got to square the cubes.
You got 1.3 and 1.5? That's a lot better agreement.
Yeah.
Okay,
No,
all right, you've been left in the dust. You're gonna finish that on your own time because we're run out of time here. So in fact, this is right. I got 10 to the 10, but you know. 10 to the negative 10, but this is about the same. So let's think about what this physically means. So how long does it take for the atom to decay?
not long.
Basically,
Basically instantaneously, right? So why is anything?
There's
It's
so
Therefore-
much-
Therefore, atoms aren't following the Bohr model, otherwise nothing would exist.
Exactly, so that's the only logical outcome, is that everything must be the plum pudding model, right?
Totally.
Yeah. And everything that we've learned before in modern physics is a hogwash,
One.
right? Why do we even do it? No, so some of you are in quantum, so what's the real solution? So remember that probability clouds are a way of our interpretation.
Is it not moving?
Yeah, so here's the question, is the electron moving?
That's what I'm saying.
Yeah, no, I'm answering your question by asking the same question.
You think? I
Does
always-
the electron move?
I always thought.
Not the same way that we would expect it to.
Yes and no, right? So the atom is certainly, the electron certainly is moving. But it's only allowed to release or gain energy in quanta. So when we talk about quantum mechanics, it is the fundamental assumption, or it's an axiom, that says that energy can only be gained and lost in quantized amounts. And there is a fundamental quanta, which would be something like h bar, right? So you can see that when you do your quantum mechanics, that there are these energy levels and they're separated in 1, 2, 3, all these integer levels. Okay, so even though the atom is going around and it's accelerated, or sorry, the electron is going around, it's accelerated, it's not allowed to lose energy because it can only lose it in quanta. Does that make sense? No, that's the correct answer, is that it feels very uncomfortable, and it should make you feel uncomfortable, because nothing that we do in life is this way. So the way that we always are supposed to think about it is if you have some stairs, I can take those stairs 2 at a time, but I can also like raise my foot halfway up the stair in order to get to the next one. So the way that we think about the electron inside of the atom is that if you stood at the bottom, you can only be at the bottom or the next stair and at no states in between. Right? In order to get up, you'd have to go boop, 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 boop. And the only way you can do that is by getting energy. And you can only get energy usually through photons. There's a few examples of collisionally induced ionization, but that's unusual. Okay. So now you've understood what the problem was, right? At the beginning of the turn of the century. This is why people said, well, something's really wrong here. There was another major problem, which is called the ultraviolet catastrophe, which is what happens when you begin to turn on an oven. Classical statistical mechanics should tell you that you get an infinite amount of ultraviolet radiation. And in fact, we don't ever see that. So something was broken. And the same answer was that you had to quantize. So everything was screaming, you have to quantize, okay? All right. And this works really well as long as we're moving non-relativistically. We can begin to start to think about special relativity. Are there any questions about like this type of work, radiation, before we move off of it? Yeah, no? Okay. All right, yeah, let's finish with some of the okay. I'm gonna get rid of some of this. We're gonna think mostly about these, go back to this example of why is there blue light in the nuclear reactor? And should I go touch it?
Yes.
No. Don't ever swim in blue light water, okay? Very dangerous. All right, so the first thing that we want to ask ourselves is, so what happens, we'll think a little bit about that radiation pattern, which was this like cone of light that was coming out. Let's write down. Let's write down the total power again. P, and we're mostly doing this so we can get used to some of these terms that we're about to see far too often. So we're gonna write this thing. I know that that's upsetting, but don't worry. All right. So I pulled a really fast one on you. We're gonna need to get used to this one here. What's this one? Gamma. Gamma, yeah, and gamma is. Haven't seen special rotation before? Yeah. No, yeah.
Something minus.
In
Isn't it
one,
like 1 minus beta squared?
one minus,
Yes.
Oh, well, do you want like what beta is?
Yeah.
Oh, V over C squared, quantity squared, excuse me.
good job. Okay. So this is, this also has a name, everything has a name in physics, right? Because someone did it. So this is called, Grignard's generalization, that's an R. Something like that says generalization, okay. So this is gamma to the power 6, radiation goes up fast with velocity. So what do I mean by that? So how does gamma behave? Let's say that V is close to 0.
Then gamma is boring,
Gamma's boring, very good. Gamma's what?
1.
1. All right, and as V approaches C, infinity, right? Right, because this thing is blowing up. So this thing heads towards infinity. So this is very sensitive to the velocity. And in fact, this thing is blowing up to infinity as V heads to C. And what's the power that we have in here? 6, okay, so this thing is blowing up, okay. All right, so let's take a particle. Let's try to accelerate it to the speed of light. Right? As I try to accelerate it to the speed of light, what does it do? Kind of, I mean, not really, it doesn't explode, but it starts putting off a tremendous amount of power, right? Its gamma's out there to the 6. Okay, so we can write this, essentially. Shit, we're running out of time as always. Let me just draw how the radiation gets beamed here. So this is V. So this is an image when looking from the side. This is how the power is getting beamed, and it's really cool. It's these fun little like butterfly wings, right? And the power is heading out like this. So you end up with something that looks like dP dr is sine squared, well, I should say like this, approximately sine squared over 1 minus beta cos theta, the 5. There's a different value in Griffiths, but these choices are mostly commensurate with one another. The important thing that you're thinking about here is this is how the radiation, well, I can write it here. This is how your Brem prolong this is how Bremsstrahlung radiation is distributed. And what you're essentially looking at here is particles are coming in, let's imagine a situation where you have a nuclear reactor. You have fission, right? And the particles or the uranium atoms or plutonium, what have you, are breaking apart. And they're releasing very, very energetic electrons. And those energetic electrons basically travel directly out of the material, and then they hit water cooler, and they begin to slow down right away. And as they slow down, right, this acceleration comes into play. Now, they started with tons of kinetic energy. So this was very hot, right? And so as they slow down, they will change the frequency of the light that they put out such that you can see it with your eyeballs, right? If you're in that water, you're dead. But interestingly enough, if you're at the top of the water, you're fine. You can swim. Yeah, go ahead.
Like, what exactly would happen to you other than death? Like, how would the death happen if you got killed?
Badly, real badly. Radiation poisoning is nothing to mess with.
Yeah.
You know, your body, I'm not a biologist, so you're not gonna quote me on this, but you can basically live for a few hours, right? But all your skin will slough off, all of your internal organs will dissolve inside. You know, I would recommend Midnight in Chernobyl, which is the book on this topic. But there's also an HBO series, which does a pretty good job. It's a mini series, I think it's 3 or 6 episodes, and they do the physics correct. But as a student, you know, 2 of the books that I always recommend to people are Midnight in Chernobyl for understanding the cataclysms that are associated with nuclear energy, and when we fail to understand the world, or when we fail to understand the universe. I forget what the name of it is, but that's a shorter book. And it really goes into a myriad of topics about the intersectionality between physics and ethics, both of which are really important, right? As physicists, the thing that you have to remember is that we're talking about nuclear energy, we're talking about things that can kill all of humanity at once, right? So we have a moral obligation to understand the ramifications of that. You don't just let nuclear waste go out into the ocean, as fun as it might be, right? Okay, so swimming in something like this would be catastrophic if you go down. If you're at the top, you're fine. And the reason for that is if you can see the blue light, you're probably fine. If you can't see the blue light, you're in a lot of trouble. And the reason for that is because if you can see it, it's slowed down enough, right? Similarly, we have an entire detector array which looks for cosmic rays. Have you heard about this before?
No.
Yeah.
What's this called?
Did I recently just get something big?
Yes, okay, so every time that I teach, I always have something comes out in the news, comes out on Twitter, and I'm like, oh, I could just highlight that, because that's a great example of what we're gonna do. So in fact, we use the atmosphere as a detector. And what happens is that we have cosmic rays, which have tons of energy. They hit the top of the atmosphere, and they slow down, and they create a cascade of particles. They bump into stuff that accelerates other stuff, that bumps into other stuff, that creates braking radiation that we can see from the ground. We just use a collection of cameras on the surface, looking up at the night sky. And we saw this one particle. Now remember, this is a particle. One individual particle, cosmic ray, have as much energy as a brick. Someone threw a brick. Now you say to yourself, that's not that much energy. But you forget that a brick has 10 to the 28 atoms in it, right? You throw a brick, that's quite a lot of energy. And we have no idea how it's created. Zero idea. Breaks all ideas of modern physics. Yes, that's amazing. It's pretty fun. And so this is how we see it. We see it with Berm's law. Okay, I'm running out of time here. Wait, what is important? What is important? Oh, okay. So when we think about this in the context of the Earth, the places that you see are nuclear reactors. You see it in the cooling stations of nuclear reactors. Where we see it in the universe is in the cooling of the ISM, the interstellar medium. So we have cosmic sources, and this is actually a major source of opacity. So if we look in the stellar atmosphere, you have hydrogen ions that are absorbing this radiation. So we're actually not getting all of the light because you have these protons and electrons. This process that we talked about, this braking radiation, goes both ways, right? This is a time-independent object. So just like we saw radiation come out of things that are slowing down, you can also imagine that any particle, if properly attuned to this, could grab some radiation and speed up. Does that make sense? Right, all the physical processes. Okay, so that exactly takes us to relativity. And it also takes us out of time. Any questions before we finish today? So for next week, you're gonna have the homework that was supposed to have been assigned over the break. That would be chapter 11, and it's just 2 problems, but it's the ones that we started in class. And then the special relativity homework will be due like Thursday, the finals week. Okay. Cool.
Yes.